So today we will be continuing talking about dynamic programming. Last time we talked about very simple tasks, and finally we finished with longest increasing subsequence. Today we will be improving some, solving some other problems, and we will have the lecture tomorrow also at 5 in 229 auditorium, as far as I understand. This lecture, I think these two lectures will be a little bit short, so, but quite important. So they can be short but important. Okay, let me start with longest common subsequence. So what is longest common subsequence? You are given two strings, this one and this two, and you have to find the longest subsequence of these two strings that are equal. So for example, I don't know, Baras and Ananas. So the longest common subsequence is 3. So this AS, for example, like that, or it can be like that. We don't care, like this is the subsequence, so we don't really care about whether there are consequence symbols or not. Like also we can do like that, for example. This will be the longest subsequence of these two strings. So do you have any ideas what their state should be in this? So I want to remind you how we deal with dynamic programming. We have state of the dynamic programming and there are steps on how we recalculate it. So what do you think will be their state of this problem?
Well, it should be something with the position in two strings. Maybe we'll have some pointers in them.
Yeah, okay, good. So we have two pointers. DP, IJ. Okay. Can you tell me what will mean DPIJ? What this DP will mean?
Maybe it could be something with the longest subsequence that already is there.
Yeah,
in the practice.
Yeah, exactly. So this is LCS, longest common subsequence of S1I and S2J. Longest common subsequence of these two strings. Okay, how to recalculate? What steps do we have here? So yeah, so let's consider it. Like we have there already. We have a rectangular grid. So we have I and J here. So we want to calculate this guy. What are their options?
So if the elements are equal, if the characters are equal, we can increase our DP.
Okay, and from which state we should go?
Well, the next step would be to move the pointers forward, but
yeah. So suppose we want to calculate dpij, okay? We want to calculate dpij from which. So you're quite right that we kind of can consider only last characters of this substring. Like if they're equal, then what does it mean? What is their step will be? From which state we will go to this state?
Well, we could go to this state either from the I minus 1j or from I j minus 1.
Okay, from here.
Yes.
Any other? You haven't done exactly what you said. So what this move means? It means that we added a symbol, but we didn't increase the longest common subsequence, because we added kind of one symbol here, and we added one symbol to, like, there is, you know, here, and there is an option where the symbols are equal. So from which state we will go?
Yeah, actually, I don't quite get. I thought that we moved
so
by one symbol. And
we move from here. So this is the state when two characters are equal. So what does it mean? So like this two last characters are equal, then we kind of cut them out, and what we are left is S1 I minus 1 and S2 1 j minus 1. If they're both symbols are equal. Like this moves from top and from left do not change the dynamic. They kind of, what if we added one symbol to the guy and obviously the answer will not increase? It is either dp here or dp here. So let me write. So dp ij equals to maximum of three things. So it is dp I minus 1j, it is dp I j minus 1. This means that we never matched anything, like our last symbol hasn't matched with anybody. And if si equals to sj, then dp I minus 1 j minus 1 plus 1. Does it make sense?
Well, I guess it does. So we, on this state, we update the previous DP where they matched. So when we are at I.
So kind of we consider two last symbols. If they do not match, then we can throw one of the symbols out and get the dynamic programming for the shorter strings. If they match, then the answer will be on one bigger than when we throw away these two characters, because they're equal and we kind of remove them both. So, and this is how you recalculate dynamic programming. Is it reasonable?
Yeah, I think I get it. Yes.
Okay, great. I mean, you almost right. You was almost right at the beginning that if they're equal, then we can increase the answer. But the only thing that we should move from, not from the top and from the left, but like kind of throw away both of these symbols. Okay. This is longest common subsequence. Do you have any ideas how to restore an answer if we want to find the longest common subsequence itself?
I think we should just get the last of the DPs.
Okay.
And M's. Well, the right bottom corner.
Okay. Okay. This will be the answer. But if we want to reconstruct the subsequence itself, like yeah, the answer will be here at the largest position. But how to recalculate? We talked a little bit last time about how to restore the answer.
Yeah, I think I forgot how we did it last time.
Okay.
We stored something.
Okay, yeah. We created a special array from ij, which tells us from which state we got to here. So, for example, if they're both equal, then and you have like the previous state is I minus 1, j minus 1, then this means that we took this symbol and we have to add it to the answer. If it is I minus 1j, then we just go to the I minus 1j state and we don't add any symbol. And vice versa, if we got from this guy, then it's also nothing is added, but we moved one symbol back by the dynamic program. And that is how you restore it. Like the answer for this string will be what you need. Okay. I think this is it with longest common subsequence. Now we will talk a little bit about Levenshtein distance or eddy distance. This problem is already quite popular in biology. Levenshtein distance. So right now, we want to transform one string to another string by making 3 different operations. The first operation, change symbol. The second, remove symbol. And the third one is add new symbol somewhere. We have this operation. So for example, for this guy, for example, we replace B to A, replace R to N, and insert N here. Okay, we replace B with A, R with N, and insert a new character here. Everything else, like then their Levenshtein distance is 3. Of this, because we did 3 operations. So this is already coming from their biology, to be honest, because like typically we consider 2 genomes and we kind of want to find how many we should change in one genome to get another genome. So in biological style, the change symbol cost like change symbol from change from X to Y. Then we have remove symbol, like the cost of remove, like let it be the cost of change is C, the cost of removing a symbol is L, and of adding is A. So right now we have kind of weighted operations. So, for example, it's typically typically this change symbol is also has different cost for each pair of symbols, because for example in the biology, for example, A to T is easier to get than A to G, something like that. So kind of like G and C like cheaper, while with other pair they're more costly. So what do you think will be our dynamic programming here? The state?
Well, the state could be once again those pointers.
Okay, good. The state 2 pointers. But what now the state means?
Well, the dynamic programming,
Yeah.
It would be the minimal cost, I guess.
Yeah, the minimal cost to get the prefix I
Yes.
to prefix G. Like, you should understand why it should work, because kinda their strings are going from left to right, so like if you match the prefix to the prefix, then kinda you're fine, because in the answer you will be matching the prefix to the prefix anyway. Okay. So now we want to make it as cheap as possible. So now we want to minimize the distance. So what will be the recalculation? So again, we have this strange matrix, rectangular. So we want to calculate the answer ij. So what other conditions here?
Well, I guess maybe it's all the same as we had the previous time.
Okay, can you tell me then?
So,
oh, let it be, this is stringed S1 and this is S2, so to be more clear.
So we could have moved from the I-1j or j-1.
I-1j. What cost we have here? Right now we already have costs. Oh, sorry, from I-1j, you told me. From I-1j. What does it mean? So which operation are we doing here? So it is obviously not change of the symbols, because the change of the symbols will be I-1, j-1, because we will take two symbols again. So it is either remove or add.
Well, I guess we add to j in this.
No, we kind of trying to do from S1 to S2. We want to change S1 to S2. So
okay.
what we will do with the symbol? Let's think a little bit.
So yes, if we want to change S1 to S2.
Okay, let's write a little bit. So we have we kind of matched. We want to match these guys. Instead of that, you had this. I think no, it didn't clarify anything. Yeah. So I mean, this symbol is already at S1. It is already at S1, and we know that it doesn't match the guy at the bottom. So what we should do?
Well,
I mean, it's quite simple, because
yes,
this symbol is already at S1 and it doesn't match anybody in S2.
so we should remove it?
Yeah, so we should remove it. Then, from the left, what we should do?
Then we should add this?
Yeah, because this symbol is in S2 but not in S1 yet. So we want to add it. And here, from here, it will be a little bit more complicated. So let us write. So we want to calculate dp mean from dp I-1j plus r, dp I j-1 plus a, and what with the last condition?
Well, I guess the only option left is to be changing the symbol, but
Yeah, but sometimes you do not have to pay at all.
if they are equal.
Yeah, if they are equal, you don't have to pay. You don't have to change anything. So here is if Si equals to Sj, then please take dp I minus 1, j minus 1, or else change me one character to another character. That's it.
Yes.
I mean, it's a little bit complicated to write, especially if you want to have, if you want to restore an answer again, you want to know their sequence of their actions that you have to do to the string to get from one string to another string. You again have this from, and you have to consider three things: either you remove or add, or you add, you change the symbol and check what you need. Okay, questions about this part?
Yes, I guess it works. Yes.
I mean, this is important. Like, this is important because it appears in it appears in their algorithms in bioinformatics. So if you're not stuck on that, there are several improvements of that. Oh yeah, what is their complexity of both of these algorithms? Levenshtein distance and this one.
It should be the product of the length.
Yeah, it is the product of the length, yeah. Now let us talk about another problem, we will consider today three different dynamic programming approaches. So this dynamic programming was taken similarly to the turtle that we did last time, but their states are a little bit different. So there the state was obvious, that the state is their position where currently the turtle is, while here the state is a little bit more complicated by their logic that appears to be in that dynamic programming is the same. So the next problem is the problem of LaTeX spacing. So what does it mean? You have a list of words. So you have word 1, word 2, word 3, and etc. You have several words, and you know that each line can contain W characters. So what's happening there? You just take the word V1, then the word V2, then word V3, then there is some word 4, word 5, word 6. Let it be the huge word. I think this will be V1, V2, V3, V4, V5. So in the Microsoft Word, for example, if you take this distribution of words and you set broad to the whole width, you will have this three will be equally separated, etc. But it will not look very pretty. LaTeX uses a little bit different thing. It calculates their spacing penalty. What does it mean, spacing penalty? It takes the spaces here And if the space, for example, this space is s of length s1, then it adds of s. Then it adds s cubic to the target penalty function. So because of that, for example, LaTeX will put this guy to this line. So not like the Microsoft Word, which does this, and it seems to be a little bit prettier. So it appears that this problem is also in dynamic programming. So you want to understand what is the total minimal distance given these words and W. What is their total minimal distance you can achieve by adding the words in lines. The first question, what would be the state? The problem is clear?
Yes, yes.
Okay, yeah. So let's think about the state. Yeah, it's a little bit more complicated than we thought previously.
Well, I think the value of the dp itself would be the minimal distance.
Okay, that's
Yes.
reasonable, right? But what will be the state?
The state, I think it should have something to do with the words distribution over the lines. So maybe it would be the number of the word and the number of the line on which it is placed. But
Okay, please think that we don't need to do anything with lines. Kind of, we don't have the target as their smallest number of lines. We just need the spacing. So what can you come up with there?
but I thought that the width of the line was our
It's
constraint.
Yeah, but you don't need to minimize the total number of lines. You just have to minimize the penalty. So it doesn't matter how many lines you had for some prefix of words.
Well, then maybe we could just take the word number.
Yeah.
Like,
Okay, so that's good. So like the dp will be dp of I. Would it be? Is there smallest penalty of what?
well, the smallest penalty of the words which were before that.
Okay, put in I words.
Mm-hmm.
Put in I words. So, and we would think here that's the place where the line stops. So, kinda. Yeah. What other steps? So if we know that dpi is the smallest penalty, put in I words, that these I words fit all the lines. Like we don't know how many, but they fit all the lines.
Mm-hmm.
So what can be the step from how to recalculate from the future or from the past?
Well, we should try to add this word to all the previous words, and maybe see if it fits into.
How? We don't know exactly how many words were in the last line. On the previous line, we don't know which words are using this dynamic programming. We don't know the number of words at the last line.
Number of words. Well, but we have all the words before this, and we have all the penalties, I guess. Well, the smallest penalty.
Yeah.
So if we add the penalty to the sum of the length and divide it, well,
No, this means that these I words are here. They stop here, right? So when you add one additional word here, you have to recalculate all the penalties that are here. Okay, so the first question. Suppose that we know that line contains like word L plus 1, and etc. word R. So do we know the smallest penalty that we will be achieved? Like suppose we know that at the line we have these words. What will be the penalty? What do you think?
well,
How we should place the words here so to minimize penalty?
well, we should make the smallest possible intervals between the words, I guess. So we.
Yeah, but how to do that? So you know the length of the words, and that's it. That's you don't know anything else, and you know the number of words. So
well, if
how should we separate, like how we should separate this, like all these spaces? Are they equal or are they not equal?
Yes, I guess it will be. Well, the smallest penalty in a single line would be if all the spaces are equal.
Yeah. So if you know that all the spaces are equal, then you take W minus, like this W, minus the length of these words divided by R minus L plus how much? Minus L plus 2 cubic times R minus L plus 2. So kinda you equally separate, you know, the size of the distance between them. You take this power of cubic and then you multiply again by the number of spaces. So this is the total penalty that you get when you know that the words are from L to R. So let's come back. So we know that dpi is the smallest penalty put in I words, so like they feed the line and finish. There will be no other words in that line. So what are the steps?
Well, do we when we step into this I, do we add the word into the same line, because it seems like we can't always feed it into this same line.
Yeah. So what? Yeah. So what will be the nice previous state?
Well, the good state would be if this word fits in the line. So we just take the previous penalty, and then add the word to the line, to the last line, and recalculate the penalty with this word in it, with equal intervals.
Yeah, so then I mean that's the good thing, but it is not enough for you to store only I. Because you have to know what words are there. So what do you need then? Like it should be with the state should be squared.
Well, maybe it would be the words in the last line.
Yeah.
Number of.
Yeah, exactly. So like this is n, where n is the number of words on the last line. So then you can add one symbol. You can check whether the new word is coming to that line or it is creating a new line.
Okay.
So you kind of come from I minus 1, n minus 1, or it's coming from I minus 1, 0.
So we are looking only at the last line.
Yeah.
So there wouldn't be a case where we insert the next word and it appears that we should move some words from this line to some of the previous lines. Well, yes.
I mean, you can add them word by word and maintaining the dynamic programming that we consider this number of words and how many of them are at the last line.
Okay.
We don't care about anything else. We just, when you add a new word, you just recalculate the penalty. You have to decrease, subtract the previous penalty and add the new one, given that it will be from I. So previously it was I minus 1 to I minus n. Now it is W I minus n, 1 W I minus 1 and W. So you have to subtract this penalty and add back this penalty and consider the minimum out of that. Okay. There is a little problem with that, with this approach, is that you have to do the two-dimensional dynamic programming. Is there any way how we can reduce the dynamic programming from here, like that we want to have 1, so kind of I is the total number of words. It's almost the same as you we want to take the last number of words at the last line to consider not as the parameter here but as the step. So let us coming from I minus 1, I minus 2, and I minus m, or so. So we kind of go over all the previous states. So suppose we are coming from the state J, and then we know what are the words, we add words line by line. So dpi is the total penalty if we feed this I words in several lines. And now we want to iterate over all the possible number of words in the last line, in the previous line. So kind of does it make sense? Kind of we have here we are kind of vi minus 1 and etc. vi minus n. So we know that we add like kind of this is exactly where we stop. So we add the ith word and the line stops here. So let us iterate over all the possible lines that can be here. What I mean by that is that I mean there can be only this word, 2 of these words, 3 of these words, 4, and etc.
In which line? In this line?
Yeah, in this line, in the last line, kind of we iterate over how many words were in the last line.
Okay, during the step.
Yeah. So our step will be not one word, but it can be taken from several states. From several states, and when you like the pretty part of this algorithm is that given vi minus n to vi, we know what is the penalty in of 1 with constant complexity. That is why it is working fast. So like we come from, we consider, did we add only 1 word in that line? Then the previous has finished the line on I minus 1. Then the previous has finished on line I minus 2, and we put 2 words at the last line, and etc. So kind of we did exactly the same dynamic programming as you told us, but we add not by 1 word, but we add like the bunch of words at the same time. The idea behind your DP and this DP is minimal. The only improvement is that we get rid of the second state, the second part of the state. Does it make sense?
Well, I guess so. So do we, when we get our final answer, the minimal, the minimal number of words, which would be our way to this answer?
You want to restore. You want to restore the answer. So let us, when you calculate this DP, let's say from I, is there how many words we put on the last line to get the minimal number of penalty. So, and that from you just get, from I, you know how many words we have at the last line. Then you just go for the previous state and check, oh, how many words in that line? And you go there, and then how many words in that line, and so on. You just restore it. So you just store how many words you added, like during the previous. Okay.
Okay.
Okay. Wait. So the next problem will be about DP on segments. This is a little bit hint how we will solve this problem. And the first problem will be, we are given some sequence of brackets. and you have to check what is the longest common, or what is the longest correct subsequence. So for example, here the longest common subsequence will be 4. So we want to calculate the longest correct subsequence, that of their given line. Please note that let me give you two hints. So at first it is DP on segments. So like you should think that you should understand that DP state is the segment. And I want to say that so each correct bracket sequence can be constructed by in two ways. It is either constructed as two other correct bracket sequence that are that we just joined them, and either you add 2 brackets outside. So let's think how to solve this problem. I think these two hints should give you their idea on how to solve this problem.
Well, I guess if it's segments, we would have the matrix in our DP, which would be ij, which are at the beginning and the ending of our segment.
Okay, and what we will store there?
Yes, and there will be the length of the longest correct bracket sequence.
Length of the longest bracket sequence on this substring. On this substring. Okay.
Yes.
Okay, good. We know the states. Now we have to understand what are the steps should be of this dynamic programming.
Well, to increase the DP, we should either from the second hint, we should either go to I-1 j+1. It's the second case, or we should
similar, but like okay, we right now want to calculate ij, right? Answer. So let us consider 2 cases. So like we take this one, right? So we move from which state? So this guy is moving to which state? DP.
Well, I thought that is from the I-1, so the left bracket, and j+1.
No, we're like kind of. Let us do this in the forward manner. So we want to calculate from the smaller.
Oh, okay. So it will be, yes, it will be from then
I+1,
yes,
j-1, and only if si equals to open bracket and as j equals to close bracket.
yes.
Okay, what should we do in this case?
Well, in this case, it should be either so j-2 or I+2, and the same other dimension.
Not exactly. The length of these substrings are not necessarily 2,
yes, yes.
right? So I mean, the previous problem should have kind of give you a hint that there can be non-constant number of previous states. Like previously we had like the constant number of previous states, and like that was the problem. But right now their states are not necessarily constant. Their number of steps. Oh, yeah. So here's +1 by the way, because we matched one more in the bracket.
Well, in our step, can we iterate through the j, so we have some state with ij, and we then have to.
Yeah, exactly. We have to kind of we know that the answer for dpij is there either this guy or the concatenation of two substrings.
Yes.
So we just iterate over all k and consider dpik plus dp k plus 1 j. So like we iterate over all 4 k of I plus 1 till j minus 2. So we just iterate over all the things. So like, okay, we did how to calculate dpij. If we do this, for example, recursively, or like we just go over all, we will kind of fill everything out. I mean when you call this call ij, like as we did with memoization, and we will call like 1n, which is recursively will find the right answer. If you want to get rid of the recursion and etc., you have to properly iterate over these substrings in the right manner. What would you think the right manner of this substring? So like, I mean, if you want to calculate ij, we should know all the answers for all the strings that are inside it. So what is the right? So what will be the right order to iterate over their substrings, subsegments?
Iteration, you mean in the first case that was k? Or
So okay, let me see. Like how you will typically do that, right? So for I from 1 to n, for j from 1 to n, then dp ij equals to like conditionally equals to dp I plus 1 j minus 1 plus 1, or we can for k of I plus 1 blah 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 to j minus 1 dp j minus 2 dp ij equals to maximum of dp ij and dp ik plus dp k plus 1 j. Something like that. That would be our target algorithm. But the issue, if you iterate over like that, for example, at the first, like for example, we have I equal to 1. We come here and we want to calculate, I don't know, 1 to 4. And you compare the symbol 1 to 4 and want to know the answer of dp 2 to 3. So it was one for here, and it suddenly becomes 2, 3. We don't know the answer for 2, 3 yet, because we never go by this for loop previously. So the question is, what are the right order in which we should care about our segments? So what is the difference? Like, we have segment ij and we have segment I plus 1j minus 1. Which component of them we can order them on? And here, like, can you find there some property by which all the segments on the right are preceding the segment on the left? Is there any property there?
Preceding? Well, I see that the j is always smaller than on the left, and the ith, the first component, is always.
Okay, probably I.
Is that what it is?
Hello, Twitch Sawyer. Okay. Let me give you a hint. So yeah, I think it's not clear what I'm trying to ask. So you can see that the length of the segments is smaller on the right.
Okay.
Okay, right? You see that this segment is smaller by 2, and this segment are smaller by, I don't know, some value, but they're definitely smaller. Okay, so what iterations should we have here?
Well, I guess that we should somehow at first take the smaller segments and then take the greater segments.
Exactly.
I'm
So
not sure how to do that.
That's pretty simple. So suppose we have we kind of calculate len. I will explain why from 3 a little bit later, but like right now. So we just let's iterate over the length of the strings and consider here from position I. Then you know that j here is I plus len minus 1. Okay, if we fix the length and we fix the first symbol, then we know where the last symbol is of this, and then we can do exactly all as we wanted here. Is it clear?
Yes.
Right now. Okay, great. This is all. We are almost done here. So you can see that when you come to everything on the right was already calculated because we iterate over length. So they're already calculated under the previous steps. The last question is to get the proper initialization. I think from one it will be fine. No, let it be from the length from, yeah, let it be from 3. So we have to fill all the dp I and dp I plus 1. So the first guy is always 0. Like you have just 4, I equal from 1 to n. Like these are the segments of length 1. So you never can get their correct subsequence. If it is of length 2, then you have two options. Either they're matching or they're not matching. So it's either 0 if si equals to si plus 1. Oh, sorry. Equals, not equals. It is 1 if so, and if 1 as I plus 1. I mean, equals is the sense that they're matching. So, and that's it. That is what you get from the dynamic programming as you wish. This is why it's DP on segments. So like you have your dynamic programming is over segments, and you have to calculate that. How to, like, the question is how to restore. Is it clear how to restore? If you want to restore the longest sequence, that is correct bracket sequence.
Also our from, I guess.
Yeah. So we just stay from either this or from K, where you know the position where you split, and then you recursively get the answer. Okay, good. Let's continue with DP on segments on another problem.
Is it true that the whole table is filled in the end?
Yes. I mean, not the whole. Their upper triangular part is, because J is always bigger than or equal than I. So it is halfly. It's halfly filled. Yeah, at the end we will have like everything is calculated. So yeah, where is the answer?
Well, it should be from the 0 to the length.
Yeah. Not the length to n minus 1.
Yes.
Because we kind of I, J are both should be the ends. So let us consider the following problem. So you are given the matrices A1, A2, A3, AN. And you know that these matrices have the right dimensions. What I mean by that is that this one is n1 n times 2, this one is n times 2 n times 3, this one is n3 times n4, and etc. So you can kind of multiply them in any order, but from left to the right. Okay, and the question is, you know there is sizes of the matrices, and the question is how many operations, what is the smallest number of operations that we should spend on? So for example, if we merge this if you multiply to these matrices, their multiplication is equal to like that. It's just their multiplication of the sizes. That term. You have three sizes kind of here. You have n2, n3, n3, and 4, and the multiplication of these two matrices. I think you know that it can be done in this number of operations. So you have to answer. Yeah, you have to answer what is the smallest number. Like we can multiply these matrices in any order. Like we can, for example, multiply these two matrices and for example to this and then and so on. What is the minimal number of operations that we should spend on multiplying all these matrices? ideas?
Well, I guess when we have the matrices, the choice that we have to make for a segment of matrices is whether we want to do the left or the right multiplication first, and between them we should, I think, choose by which size will be collapsed and which of them is the maximum. So we want to collapse large.
Not exactly. I mean, close, but not exactly. Yeah, like the first part is brilliant, so that this is dp on segments. Like that, dpij, it is the minimal number of operations to multiply by ai ij. Okay, so that is clear. Then, what are the steps here? So, consider their last operation that we did on this segment. What it was? The last operation that was done on this segment. It was multiplication of some two matrices, right?
Yes. Well, so it's either was.
No, not exactly. Okay. So if you have A1, A2, and 3, A4, you could multiply A2. Like you can multiply this, multiply like this. So you can multiply this two, then you can multiply this two, and then you can multiply the resulting, like, two parts. So it is not about the leftmost or rightmost. It's a little bit more trickier.
Well, maybe we could consider all the subsegments of the current segment.
Yep.
And see. Well, the same way we did with the brackets. If we take the left matrix, so we choose the k. And
so kinda you have this A1 or AI AK. Like consider the last multiplication that was done in this segment. It is either the answer for IK multiplied by the answer for k plus 1
yes,
ij.
yeah.
So this is dp. This is dp ik. This is dp k plus 1j, and so the total cost, if we split by k, it is like sum on the left, like the answer for the left part, the answer for the right part, and what will be the complexity of the multiplication of these two matrices?
It would be the leftmost first size and the rightmost last size.
Okay, and I and j, and what in the middle? You can see here.
Yeah, so in the middle it would be the AK second dimension, or the AK plus 1.
And k plus 1, yeah. So it will be here and k plus 1. Because like this guy is
okay, yes.
and k plus 1 times and k plus 2. Okay, that's it. You are doing exactly as previously.
Should it also be nj plus 1 there? Or no? Yeah.
Oh yeah, it is nj plus 1. Thank you. Nj plus 1. Yeah. So and you are doing exactly the same as with brackets. So you kind of iterate again over the segments, starting from their smallest length to higher length. And you just do exactly the same. Yeah, the restoration is also quite simple. You just find where you split and go recursively. Then you find the answer. This thing, like there are dynamic programming on segments, you will be faced with on the bioinformatics algorithm next year. There is a problem on how you're given an RNA, so it's one strand, and one strand can do like some strange things like that. I think you've seen something like that.
Yes.
Like these things. So you would be surprised, but this two-dimensional structure can be done using the dynamic programming. Because this is exactly kind of their subsequence, like their segment which is stored from, which is calculated from other segments. It's a little bit more complicated, but still the idea is that the dynamic programming on segments. Okay.
In this case, do we also have to initialize this?
Yeah, you have to. Okay, let's talk about initialization. How we should initialize.
Well, I thought about taking just the pairs.
I mean, you can initialize like that, and that's it. And here start with the length 2, because you will be kind of to get I plus 1. You will iterate over k, which is I, and you will have dp I plus dp I plus 1 plus their multiplication of these two matrices. So like their initialization here is a little bit simpler. Okay, that's it with dp on segments. Okay, we have some amount of time. So let us think about the following problem, which is not exactly on dynamic programming, but it looks similar to. So we have a string P and string S, and we want to check whether P is the subsequence of S. So yeah, for example, you can use our longest common subsequence dp for that. If the longest common subsequence of these two strings is one string, then we are done. Okay, but it can be done faster than multiplication of the strings. It can be done in linear time. So let's think a little bit.
In linear time, you mean the sum?
Yeah, the sum. Yeah.
Should this subsequence be like the whole string? Should the P?
No, not as the substring. Again, as a subsequence. I mean, the first symbol can be here, the second can be here, the third can be somewhere here, and the line they're not necessarily consequent. Sorry.
think that this maybe could be done with just the 2 pointers. I don't see it.
Yeah. Okay. What is your solution then? It can be done using 2 pointers, right?
Well, yes, it should be. We take the point. Well, we put in the beginning all the pointers in zeros.
Okay.
And then we're kind of looking for the piece letter current. Move until we meet it, and when we meet it, we just move the p pointer to the next.
Yeah, exactly. So kind of you want the p1. You just go from the left to the right until you find p1. Then you go to the right. Then you go to the right here, and now you find p2.
Yes.
Here and so on. Yeah, and it can be done. Is it clear why it's linear time?
Yes.
Okay, yeah, because each pointer comes through each cell only once. Yeah, so that's exactly what I was asking in this problem. Okay, so we have time right now. Thank you very much for coming. See you tomorrow.